So again, we're on the back side of the worksheet from yesterday. These are computer outputs, okay? Statisticians put data into a computer program, not a calculator, and they want to do a regression. They hit a button and they get all this information. And we have to be able to tell what that information is. So the first thing it tells us at the top is that the dependent variable is fair. What does that mean? What is dependent variable? It's the y variable. Okay. The y variable is what it's telling you at the top when it says dependent variable. We're going to ignore this part, and we're going to ignore the r squared adjusted. R squared adjusted is used when there are multiple x variables and you're doing multiple regression, which we're not going to do. So here it tells us r squared. Obviously, it's telling us r squared. How do we get r from this? Our computer output is not going to tell us the correlation. It only tells us r squared. Square root it, right? So if I want r, I have to do the square root of 0.482. I have to make it a decimal and then take the square root. Okay. Then it gives us s. Okay, s is 41.82. This is the standard deviation of the residuals. The higher the number is, the more variation there is. Then it says 18 minus 2 equals 16 degrees of freedom. Okay, degrees of freedom is going to come into play once we get to chapter 27, our very last chapter. Right now, the 18 tells us n, the number of data points. We literally ignore all this stuff in the middle. And we pretty much ignore all this till chapter 27, when we actually do a hypothesis test for the slope. Okay, so that's later on. And then the important information down here is this is your B naught and your B1, and this is your X variable. Gives us everything we need to write the equation. We don't have to do any calculations other than possibly calculating R. Now, it's really important, if you're asked to calculate R, that you pay attention to the sign of the slope, because R should be positive if the slope is positive, and R should be negative if the slope is negative. So you have to make sure you pay attention to that and give R a sign. And there's a lot of people yesterday that had a pretty good estimation for R, but you didn't make it negative even though the graph was negative. Not yesterday, but Wednesday. So I graded those yesterday. And we can look at that later. Okay, so that is our computer output and what it all means. Okay, so basically the most important information is at the very top and down here. Okay, this is like the most important stuff. Okay, and that's why you'll see in your book it kind of sometimes only gives you that and then dependent variable and R squared. Okay. So it asks us in number 1, is a linear model appropriate for estimating airfare from distance flown? So we want to look at the scatter plot and the residual plot. So when it's asked if a linear model is appropriate, we want to talk about two things. Is the scatter plot linear, and is the residual plot scattered with no pattern? Okay, so we can say yes, because the scatter plot is linear and the residual plot. Okay, remember the residual plot here is all of the points, all of these points and their distance from the line, right, put on this graph. The computer outputs will put it against the predicted value, and your calculator can't really do that. So we do the x value, and it doesn't make the residual plot look any different, okay? So remember that we're looking for random, scatter, consistent spread, and no pattern, right? So the residual plot has random scatter, consistent spread, and no pattern. Okay, so when it asks, is a linear model appropriate, you're looking at both plots. Most students leave off actually addressing whether the scatter plot is straight or not. When it asks us how strong the model is, it's asking us to talk about the R and the R squared. So we're going to state what the R is. Let's calculate that. The square root of 0.482. We actually have that on the front side of this worksheet. So R is 0.694. Okay. So we call that what? Moderately strong. Moderately strong. And then we interpret R squared. Okay, we say the difference is in, the variation in distance from Atlanta explains 48.2% of the variation in fair. So when it's asking you how strong the model is, your explain is to state what the correlation is and what that means. We see it's 0.6, that's 0.69 is in our moderately strong range, right? 0.6 to 0.8 was moderately strong. And then we interpret our R squared. If it asks how confident you are in the model, you just have to interpret your R squared. So the confidence you have in the model is R squared. We're about 48% confident because only 48% of the variation is accounted for by the model. Okay. Are there outliers? Probably this guy, right? It's unusually cheap for how far away it is. Sometimes outliers really stick out in the residual plot. Okay. So why is it unusual? It has a high residual, right? It's pretty low for the given x value. So yes, that's about 600. And 145.
On the front side, it says Kansas City 683 141.
Okay, so that's what it would be. 683 141. Yeah. And because it has a large negative residual. Not all points with large residuals are outliers. But that one just kind of seems to like stand out, right? So write the equation of the model. Again, this is the same model that we had on the backside, right? When we calculated from the summary statistics, we got these same numbers. So our equation of the model is the same, but again, we're looking at these numbers, right? So it's fair hat equals 177.215. If you have all the decimal places, you can use them. It's positive, so plus 0.078619 distance. Just wanted to color code that. And can you predict the fare for a 1,000-mile flight? Right, plug in 1,000. 177.215 plus 0.078619 times 1,000, 255.834. So 255.83. So one of the questions on the quiz talked about what happens to the correlation if you switch to the x and y variables. And it said in the quiz, oh, you switched x and y, and it became a positive from a negative association. And that's not what happens. When I switch the variables, my relationship stays positive or negative. It doesn't change the direction if I switch what variable is on which axis. So my correlation doesn't change sign, and it doesn't change at all. So my correlation stays the same when I fix the variables, but it's not an algebraic relationship. I can't say, how far could I fly if I had $500? That I can't do. I can't plug that into the equation for y and solve for x, because this isn't a perfect relationship like in algebra, right? This has only a correlation of 0.694. So we have to redo the regression if we want to see, if I have this much money, how far I can fly, right? I want to fly this far. How much money is it going to cost me? That was the first equation. Now the second equation is, I have this much money. How far can I fly? I have to redo the regression, switching the y variable to the distance and the x variable to the airfare. And we get a new equation. Write the equation to estimate how far you could fly for any given price. So take a second and look at this output. Where are the numbers you need to write the new equation? Now your y variable is distance and your x variable is fare. So write the equation. What did we get for our equation?
Distance half equals 177.23 plus 6.13101.
Wait, where did you get 177 from?
Oh, I just used the old.
No, it's right here. There's a new one. Negative 644.287. It's not just the slope that changes. The slope and the y-intercept change, and the slope stays positive. 6.13101 fare. So my new equation has a new y-intercept and a new slope. The slope stays positive. The correlation is the same, right? If I had to recalculate it from the summary statistics, I would do the r times the standard deviation of the distance divided by the standard deviation of the airfare, right? Because I've switched my x and y variables. The regression output does that for you. You can see the scatter plot, right? It's still in the positive direction. Even though I put my variables on different axes, my graph is still positive and my residual plot is still scattered with no pattern. So if we look at the amount of money we got here, this is the last question. What does this model suggest, or how far does this model suggest you could fly for the fare we estimated in number 5. So we said if I wanted to go 1,000 miles, it would cost me $255.83. Okay? So if this was a perfect relationship, if I plugged this into this equation for fare, I should get what number? I should get 1,000, right? Am I going to get 1,000? Find out. Go ahead, plug that in. Times 255.834. So we'll plug that in and see how far it estimates we can go. What distance does it say we can fly? 924.23 miles. So it's off a little bit, right? It's off by about 75 miles. And that's why it's because there's variation, right? It's not a perfect linear relationship. And so we can't just plug in for y and solve for x. We have to redo the regression model. So we're back to using this data that we entered and made our lists. We're going to go stat calc 8, which is linreg a plus bx. A is the slope. No, A is not the slope. A is your y-intercept. B is your slope. Okay, so for the female height and weight, we got female weight, hat, right? I got negative 116.57 plus 3.664 female height. Yeah? And for the male weight versus male height versus male weight, did we get plus 7.2, actually 30 because there's like 3 nines, so it actually rounds up. Male weight. Okay. Now, let's talk a little bit how we interpret our slope and y-intercept. Okay, we talked a little bit about that yesterday. So, to get your linear regression out of the calculator, you just put the data in, linreg 8, whatever 2 lists you have, right? Your x list and your x list, your y list and your y list. It gives you r and r squared. I did, yes. Male height. Okay. So let's look at interpreting slope and y-intercept for the males. Okay. Slope is how much we expect y to increase for every 1 unit increase in x. It's how much we expect y to increase for every 1 unit increase in x. So we say our model predicts that for every 1 inch increase in male height, for every 1 increment we increase x, male weight is expected to increase approximately 7.30 pounds. Now I can reverse it and say I can also say our model predicts male weight is expected to increase approximately 7.3 pounds for each 1 inch increase in male height. Like I can change whether I talk about the y or the x first. Now, this is a place where our y-intercept doesn't have much meaning, right? So interpret the y-intercept. Our model predicts if the male height was 0, okay, again, not possible. Even babies have height, right? If x is 0, we expect male weight to be negative 340 or 64.40 pounds. And we'll just add, which doesn't have much meaning in this context. Obviously, you can't have a height of 0, and you can't have a weight of negative 300 or negative pounds at all. So it doesn't really have any context. But this is what it means. You still have to be able to interpret it even if it doesn't make sense in that context. Okay? So take a second and write out your interpretation for the female slope and the female y-intercept. There's another concept we want to talk about. It's called extrapolation. This is an important vocabulary term. Okay? Extrapolation is trying to make predictions too far outside of the scope of our data. Okay? So making predictions too far the scope of our data is like the minimum and the maximum. Okay? We can maybe predict, if we have the data up until 2021, you could possibly predict what might happen next year and the next year. But the more we go farther outside of our data, the more we're trying to predict the future. Right? We want to be really careful about that. And not just predicting the future. If we look at our height and weight data, we have from about 60 inches to 75 inches, I think. You don't want to use that model to try to predict how tall a 6th grader is. It's different when they're in 6th grade and they're in the 40 to 50 inches range. That's too far below where our data is. We don't have data points that include some of those numbers. Right? If we wanted to use our model and predict a value that wasn't in the middle, like we didn't have, say, anybody that was 66 inches, but our data went from 60 to 75 inches, that's okay. Our model includes that number, but when we are outside of our minimum and our maximum, we are extrapolating, and we want to be really careful about trying to make predictions for values that aren't included in our original data set. 1 or 2 below, 1 or 2 above is okay. But as we get farther and farther away, the model can change very drastically in a very short amount of time. Okay, so we don't want to make any extrapolations going too far outside, too far above the maximum, or too far below the minimum to make any kind of predictions with our models. Okay, that's all.